Hi there, my name is Arrey Ivo. I'm a master's student at the University of Venda, and today I'm going to be talking about paleoclimates. Now, my talk is going to focus on this particular outline. What are paleoclimates? Why study paleoclimates? What drives paleoclimates? And how do we measure them? Key concepts of paleoclimates also will be looked at. Case study will be checked on as well. And by the end of the talk, I hope to have brought another dimension some clarity about the habitable planet story, as well as to create an awareness about the science behind the past and current climate events. So what do we mean by paleoclimates? Now, paleo is a Greek word meaning ancient, and climate, of course, looks at the average weather conditions of the atmosphere ocean land system. So in essence, paleoclimate means looking at the past climates, the past Earth climates. And when looking at or when trying to look at paleoclimate, any analysis of past climate is based on particular timescales. So as we can see from the figure I put here in the slide, you can see how the different periods of cool and warm and periods have characterized the Earth history, ranging from the Precambrian right up to the Tertiary, where we are now. Now, I want us to look at this hierarchy of models, about the Earth development throughout its history. If we look at the first one here, which is one where the Earth began with as a result of the Big Bang, and you get the bare rock, and then you get the static atmosphere and ocean forming later on in its development, and then you get to form the moving atmosphere and ocean, which starts creating these dynamics of the paleoclimates. So we can clearly see here that the Earth history in terms of climate clearly begins from this state. I'd like us to keep that in mind as we follow up the talk. Now, why study paleoclimates? We study climates for a number of reasons. I just outline a few of them here. We can start looking at the first one, which is to provide answers to why the Earth is the only habitable planet so far, and also to be able to answer questions as such as the century as the last century, you know, has been unprecedented relative with respect to the climate change over the last 500, 2,000, and 20,000 years. And also studies of paleoclimates can also give us a better understanding on those driving factors to climate change. So let's look a little bit more about those drivers of paleoclimate. Now, paleoclimates have been identified to be caused by four major points down there in the slide. The first one being changes in the solar output. The second, also changes in the Earth orbit. And the third is the changes in the distribution of the Earth land masses over the Earth. Also changes in the concentration of greenhouse gases in the atmosphere. For the purpose of this talk, we're going to talk only a little bit more about the first and the second. I think the third and the fourth will be much more suited into another coming call talks about the planet. Now, if we go to the first one, which talks about the solar changes, the solar output, changes that have occurred throughout Earth history, this theory is proposing that the stellar evolution over the billion years of the Earth history, was 30% dimmer than it is today. Saying that as such, the radiation the Earth was receiving, back from when it was formed, was much lesser than what it receives today from the sun. And talking about that to explain the records of paleoclimates, which you can see here on this figure, don't really tire as we expect to rather see a smooth graph, unlike the peaks and the tops we find there on the paleo record. So the other theory which was put forward by Milankovitch trying to explain the paleoclimates driving forces is about this cycles of eccentricity, axial tilt, and precedence. Milankovitch said that eccentricity was actually the deviation of the Earth circular movement around the Sun, which we can see moves more elliptical than circular. As a result, which will result in changes in the Earth climate in the cycles. Also, he talked about the axial tilt, where as the Earth revolves around the Sun and rotates, the axial axis, also tilts and changes from its vertical position. He also talked about the precedence where the Earth, axis also changes orientation, as it rotates and revolves around the Sun in the form of in the form of the wobbling nature that it does. So he kind of said that this cycles, this cyclic phenomenon of the Earth as it rotates and revolves around the Sun, with these three facts could also account to paleoclimates. But then the question is, what's the periodic, what's the frequency of these cycles, and can these cycles actually match those peaks and troughs we find in the record in the previous slide, which I've just brought down to show you? I don't think so. So how do we measure paleoclimates? Depending on the time scale, paleoclimates can be measured in various forms. As we know, the instrumentation of measuring the weather has only been existing for the past 1800 years. So in terms of that, the Earth's climate for the past 4.6 billion years has not been measured with instruments, and therefore we had to look for indirect means to be able to get clues about what the Earth's climate was at the time. And so paleoclimatologists have used various methods which I've outlined here, include isotopic geochemical studies, dendrochronology, pooling, distribution, lake fabs, and polar bed. All of these methods are boiled down to what we call the proxies, and proxies are actually that natural data sets which actually mimic environmental change. And so scientists are able to use these data sets to be able to reconstruct Earth history. Now let's take a little look in detail about what. Now this slide I just put in to show all the different data sources where scientists are able to gather information with regards to studies with paleoclimates. Now with sediment cores, which was one of the first data sources where we used to study paleoclimates, the sediment cores are taken from the bottom of lakes and shallow oceans and the deep seas, and the thickness of these layers which these cores are getting, represent the different climate periods as the layers were being deposited, and this can give us clue about analysis, will then give us clue about what the climate looked like at the time. And also pollen grains are well preserved in lake and ocean sediments, which also could be analyzed to tell what type of plants were existing at the prevailing climate, and it's from there scientists can infer whether the period was either cold or warm, and also about the distribution on the Earth surface. Also, stable isotopes were used by scientists also to be able to unravel the temperature of the Earth. As we know, oxygen has the different isotopes of 18, 17, and 16. The ratios of these isotopes found in sediments can be able to give us clues on the nature of the climate at the time. And also coral reefs, which are formed at the bottom of the oceans, seas, could also give us clues about the Earth's past climate. We know these microscopic organisms usually live at the photogenic zone of the oceans and use sunlight and earth and oxygen, at the surface there to create their shells, which are basically made of calcite. And analytical studies of these hard shells by scientists usually gives us clues as to the nature of the temperature and the oxygen composition was existing at the time they lived at the surface. Also, ice cores could also give us clues, about the paleoclimate record, as these glaciers accumulate over the land surface. They can be able to trap air bubbles and also those gas concentrations which are in the atmosphere. As we can see, they have been plotted here for the carbon dioxide, the oxygen and nitrogen as they varied in the different layers of the glaciers. We can also look at tree rings, which generally give us patterns on how the Earth climate was looking like. As you can see, each ring here represents a particular period in the growth of the tree, which usually responds to the climate existing at the time. So now let's look at the key issues of paleoclimate, and we're going to begin with the first one, which is the concept of the snowball Earth, which says that during the Earth history there has been a number of periods where almost the entire surface of the Earth was covered by snow, as we can clearly see here in the figure. And scientists are accounting this, which occurred about 650 million years ago, to the changes in the concentration of carbon dioxide in the atmosphere, which usually is used as a chemical weathering occurs in the siliceous rocks. The greater the weathering occurs in these rocks, the lower the concentration of this carbon dioxide in the atmosphere. And so these changes, as well as volcanic activity, control the concentration of carbon dioxide present in the atmosphere. Now let's also look at glacial and interglacial, which is also one of those key concepts of the paleoclimates. During the period when the interglacial, where the ice sheets actually restrict the land surface, and during the glacial, where there's an encroachment of the glaciers, usually also resulting to the movement of the earth plates across the surface. During the periods when those plates are at lower equator, there's a tendency of the glaciers to encroach on the land surface, and when they're at a higher equator, they're able to also retreat from the surface. We could also look at the case study, which is the PETM period. It's a period in the Earth history which occurred in the Paleocene-Eocene boundary. An abrupt increase in the temperature of the Earth usually was attributed to the sudden release of the methane gas trapped on the ocean under ocean sediments. This was usually attributed to an increase in temperature, which caused those trapped gases to be released into the atmosphere and cause an increased temperature. Now, could there be any analogy between what happened in the PETM and what is happening now in terms of anthropogenic climate change? We definitely cannot tie any analogy, as at the time there were no humans existing, and as such no contribution to the greenhouse gases. Meanwhile, for the PETM, it was just a natural phenomenon and occurred over a long period of time, unlike now where the short period of time where humans have been existing, they were able to contribute a large number of these greenhouse gases into the atmosphere. So to conclude about this talk, it's clear that the Earth's climate has not been stable throughout the history and is continuing to change as time goes by. So we can only explain the terms of these changes based on the plate tectonics, which could be able to explain the changes in the long-term paleoclimate, and the Milankovitch cycle, which could also explain it in terms of the short-term changes. The great ice ages were also caused by this process of continental drift, like I said, and together, putting these two concepts together of the continental drift and the Milankovitch cycle, we can be able to explain the long-term and the short-term changes of the paleoclimates. Now we can be able to get some references where we can be able to get some more detailed information about the material, and also from this one. Thank you very much for listening, and cheers.